The case for a moon base. SpaceX is in the process of making spaceflight cheaper and more accessible than ever, not just incrementally, but in orders of magnitude. If Starship, currently under development, delivers on its promises, then a space-based economy is not only possible, but in my opinion, inevitable. A 100% reusable space vehicle capable of hauling 100 tons into low Earth orbit is a real game changer. By refueling the Starship in orbit, this cargo can then be transported to the moon or beyond. A permanent moon base can then be constructed as the first step before establishing a manufacturing facility off-world. The moon has important resources essential to establishing a self-sustaining space-based economy, most notably water ice in the shadows of craters. The main components of water, hydrogen and oxygen, are two of the primary elements powering rockets right now. Producing rocket fuel on the moon gives you much more bang for your buck given the 1/6 gravity of Earth. It's a relative piece of cake for a rocket to escape the moon's gravitational field. Much larger ships could be built there to haul huge amounts of cargo to orbit, asteroids or other bases on Mars or elsewhere. The moon has also abundant lunar regolith, the fine powdery material covering the surface. With processing, it can be used as building material on the moon to insulate the interiors of moon bases. It makes sense to use heavy, bulky materials locally available on the moon rather than ferrying them up from the Earth's surface at huge cost. The other great advantage of the moon is that there is no atmosphere, so that the generation of solar power is a doddle. However, for continuous power, you need to be very careful where you place the base. The moon has a 28-day rotation period, resulting in 2 weeks of continuous sunlight followed by 2 weeks of darkness at most latitudes. So you need some serious battery backup to see you through the 14 nights. However, if you locate the bases at the moon's poles, then you have permanent sunlight and close proximity to crater ice. Final bonus, the resources for manufacture of solar cells are also available on the moon. It needs to be added that there are plenty of hazards awaiting colonists on the moon. Number one is radiation. The moon has no atmosphere or magnetic field to protect humans from deadly rays. Appropriate shielding needs to be available to ensure the health of people staying there for any length of time. The low gravity might also lead to major health issues such as loss of muscle and bone mass. Artificial 1G gravity can be created using, say, a large spinning underground habitation wheel or some other device producing sufficient centrifugal force. It's going to be a steep learning curve, but I believe the lessons learnt on the moon will be valuable in providing a template for viable habitation on Mars and beyond. The moon has the great advantage of being relatively close to Earth, so two-way communication is viable, as is the feasibility of a rescue mission if required. As well as manufacturing on the surface, a factory should also be placed in moon orbit to take advantage of microgravity. In time, the benefits of working in the microgravity of space will far outweigh the disadvantages. Space is the perfect construction zone for materials that possess incredible strength, transmit information with minimal loss, form enormous crystals, or even grow replacement organs. In space, microgravity allows materials to grow without encountering walls, and it enables them to mix evenly and hold together without traditional supports. And the ultra-high vacuum helps objects form without impurities. Demand for high-tech solutions requiring higher resolutions, faster processors, more bandwidth, greater precision, novel materials, unique alloys, innovative processes, higher energy efficiency, more processors in a smaller volume, and more sophisticated tools in general are pushing materials and processes for manufacturing to the point that defects at the atomic and molecular level matter. Building in microgravity can reduce these defects. The first major candidate for making money off-world is a special type of fibre optic cable called Z-band. When manufactured in microgravity, the thin cable is less likely to develop tiny crystals that increase signal loss. When built without those flaws, the cable can be orders of magnitude better at transmitting light over long distances, such as for telecommunications, lasers, and high-speed internet. The bottom line, the lunar outpost may therefore be the first recipient of the solar system's next-generation internet. On top of that, ZBLAM could be space's first money-making export product, sourced from production facilities possibly placed in both moon and low Earth orbits simultaneously. Also, a metallic glass called liquid metal developed by NASA's Jet Propulsion Laboratory, the US Department of Energy and California Institute of Technology mixes 3 or more metals to gain twice the strength of titanium. While some metal alloys and gases can be made on Earth, others can only be developed in large quantities in the realm of microgravity. And of course, low and microgravity is an ideal environment to construct huge structures using robot technology. Already there's NASA's upcoming SPIDER mission featuring the technology demonstration of a lightweight 5-metre 16-foot robotic arm. SPIDER will enable 7 elements to form a 3-metre 9-foot communications antenna that will communicate with ground stations in the Ka band. It will also construct a 10-metre 32-foot lightweight composite spacecraft beam using technology developed by Washington-based aerospace company Tethers Unlimited to demonstrate that structures can be built in space. Meanwhile, Made in Space has been developing Archinaut, an in-space manufacturing and robotic assembly platform. The core technologies for Archinaut address all the competencies required for the successful on-orbit manufacturing of satellites. This integrated system is designed to 3D print large parts and then use advanced robotics to integrate those parts with other components and verify the finished product's structural integrity. Archinaut 1 is scheduled to launch from New Zealand as early as 2022 on a Rocket Lab Electron rocket. And as exciting as these new space construction technologies are, it's frustrating that it's taken so long to test these robots in the environs of space. Both companies are years behind their original testing schedules. Not that there's anything unusual in that in the space game. Personally, I'd like to see SpaceX or Blue Origin partner up with these companies, enabling them to prove their technology much faster. Call me an optimist, but I believe once cheap and reliable transport into low Earth orbit is achieved, demand for large orbiting structures will take off. The partnership between SpaceX and NASA seems to be bearing fruit, so a similar arrangement between, say, Made in Space and Elon Musk may make a lot of sense. Right now, it appears the most likely money-making ventures are Starlink Internet and space tourism, both taking place in low Earth orbit. However, the Moon has a bright future down the track as a research and manufacturing base for a wide range of technologies. On top of that, it would make an ideal platform for space astronomy, especially if large mirrors can be manufactured on-site in low gravity. When it comes to telescopes, bigger is better. When launching from the Earth, there are only so many ways you can fold a huge telescope to get it to fit inside a 5-metre rocket fairing. Currently, all space-based telescopes are constrained by payload restrictions of rockets. On the Moon, no such constraints will exist. Once the basic infrastructure is in place on the surface of our closest neighbour, there's no telling how many unique commercial and scientific applications will spring up. The Moon could potentially become an R&D hothouse, attracting innovators and entrepreneurs from a wide range of fields. All the necessary resources are available. We need to carry out major prospecting missions using robotic craft and moon rovers to thoroughly survey our closest neighbour. This process is already in train with a number of countries launching exploratory missions. After that, we need to develop mining technology suited to the Moon's environment. Once viable extraction methods have been proof-tested, large-scale mining can commence to produce rocket fuel and materials for construction and manufacturing of machine tools. The more raw materials that can be accessed off-world, the better. eventually making the moon colony self-sufficient and one day even a net exporter of goods back to Earth. We landed on the moon for the first time in 1969 with great celebration and fanfare. One giant leap for mankind followed by an agonising stutter. For decades since, confined to low Earth orbit like an eagle with its wings clipped. Finally, there seems to be real will on behalf of government to fulfil promises made back then. Agencies such as NASA, in conjunction with innovative private companies like SpaceX and Blue Origin, are breathing new life into manned space exploration. It looks as though we're on our way to the moon once again, but this time we're not just going to plant a flag, but we're going there to stay. Elon Musk's dream of humanity becoming a multi-planet species is taking its first tangible step.